Okay, good afternoon, everyone. My name is Andy Bond. I'm a lead software engineer at Blizzard Entertainment. I've worked there for the last 16 years. I've on games like Warcraft 3, World of Warcraft, StarCraft 2, and most recently, Heroes of the Storm. And I want to thank you all for joining me to talk about what many would consider to be a controversial subject, that is the almost always auto idiom. So before I get too in-depth, the fire marshal has asked me to let everyone know that if you have torches and pitchforks, please take them outside. It's not safe in here. If you want to form an unordered mob outside, that would be the best thing, I think. So to give you a heads up of where we're headed today, first I'm going to cover what the idiom is, in case you're not familiar with it. Then I'll walk you through a case study that I picked to try to understand the implications that it has on code that I work with. And then I'll walk through examples for how we can apply almost always auto to variables, to functions, lambdas. Then I'll take a look at how we can deal with some problems that come up with branching and looping. And then I'll conclude with a overall takeaway of kind of my observations based on this experience. So the idiom, if you haven't heard of it before, really what it's all about is trying to prefer to reduce types, try to deduce types as much as possible rather than using explicit types. It leverages new C++ 11 and 14 keywords like auto and decal type auto. It's primarily been put forward in the community by Herb Sutter and Scott Myers. And I think Herb's quote sums it up pretty well here, that the intent is to write code against interfaces, not implementations. When I took a look at trying to see how this could be applied in code bases that I work with, and talking to the rest of my team, there was a lot of concern, quite understandably so, about the impact that using this style would have on code readability versus flexibility. So since I'm from a gaming background, I picked a very simple game to try to understand the implications that it would have on code bases that I'm familiar with. So we have a very simple game loop on the right-hand side, which will form the core of our evaluation. And the game just starts your player at a maximum amount of life, and then you cast one of two random spells each turn. Each spell will either increase or decrease your life, and then the game ends when you have no life remaining. So here's the definition of the game struct that we saw used on the previous slide. Pretty straightforward. Again, this doesn't have any almost always auto principles assigned to it yet. This is just a framework for us to talk about the effect that that's going to have. So at the top, I have an alias named life, which is currently an unsigned integer. Below that, I have a maximum amount of life as a static const property of the class. Underneath that, I have the default 32-bit unsigned 32-bit Mercian twister pseudo-random number generator, which I'll use to do a variety of random choice in the program. Underneath that, I have the current value of life, which is default member initialized to the maximum amount of life. And then finally, I have three functions that will help us to understand how almost always auto can apply to them. Two of them are spell functions, heal and hurt. They both take a life value as an L value reference and then return it back out. And then finally, the turn function, which we saw on the previous slide, just simply returns a Boolean to indicate whether the game should continue. So here's the implementation of the heal and hurt function, nothing very sophisticated here. I've had to add an extra alias here for uniform int distribution just so that everything fits on the slide. So inside each function, we define a uniform int distribution, which either will pick a random value between 0 and the missing amount of life, or 0 and the current amount of life. And then it'll either add or subtract that value as we go forward and use these spells. And then finally, here's the turn function. It declares an alias at the top to kind of hide the nastiness of the pointer to member function syntax. We define an unsized array with each of the two spell member functions inside of it. And then below that, we have another uniform int distribution, which we're using to try to decide which element we're going to pick from the unsized array up above. And you can see that we're using the uniform int distribution underneath that, and then dereferencing the pointer to member function, and then calling the life, passing it the life value, checking that the result is greater than 0 to decide if we should continue. Okay, so when starting to apply almost always auto principles, I kind of followed these general guidelines. By the way, for any code that you see on here, it's all on GitHub. There will be a link at the end, and I'll send my slides out to the committee so they have those available. The guidelines I followed were to use forwarding auto as much as possible. It's very universally applicable. It works with both L value and R value references, works with non-copyable and non-movable types. In any instance where I had a variable that I wanted to make sure the compiler enforced was not mutable, then I'd use const L value reference to auto instead. And for any circumstance where I definitively want to copy or move, then I'll just use plain auto. And I avoided using pointer to auto or L value reference to auto because I felt like for the forwarding auto, that kind of encapsulates everything I need. I don't need to specifically use the L value reference to auto. And decal type auto is really mostly intended for use with forwarding functions anyway. So I started to apply these principles, and I immediately ran into trouble because the only variables that are members of the class that I can convert to using almost always auto style is the maximum amount of life. Because the standard doesn't allow you to use, to define the other two variables here, the engine and life values, as auto. I believe the reason for that, and someone can correct me if I'm wrong, is that we're concerned about potential ambiguity if you have constructors and initializer lists. So that's a real shame. The syntax at the bottom, I just included for completeness sake. This is basically mimicking what decal type auto would do, but it's not worth it to really do that. We have a little bit more luck with the non-member variables that are inside of the spell functions. Those are very straightforward to convert over. I just picked hurt as an example here. You could apply the same transformation to the heal function. It simply moves the type to the right-hand side initializer, and then uses forwarding auto. For the array of spells that I had inside of the turn function, this was a little bit more difficult to contend with. At the top, the first attempt is stood initializer list. At least that's what it deduces to, which isn't really what I want because you can't directly use a subscript operator with the initializer list. You can, of course, use stood begin on an initializing list, they're guaranteed to be contiguous, so you could use that to kind of index into it, but that's not really very convenient. Next, you might try to do to add brackets there to specify an unsized or a sized array. Unfortunately, that doesn't work either. The compiler says that's arrays of auto are not permitted. The closest I was able to get was to define an alias, which has the type there so that the braces can be treated as a constructor. But this still isn't that scalable because for each different type that you want to create an array of, you have to declare an alias. So that's not a really great solution either. The library fundamentals TS has a function that they're proposing called makeArray, which actually helps quite a bit in this case. You simply provide it however many arguments you want, and based on the number of arguments, it will create a std array using the common type of all arguments that you pass in. So I think this is a pretty useful addition, and I hope to see it added to the standard officially soon. It has a nice property as well, which you can see at the bottom here, where if you explicitly pass in a type here, it will override what it would normally try to deduce. So what would normally be a std array of 3 ints becomes a std array of 3 doubles. Even though many of the many of the make functions are likely to go out of style with C++ 17, I think this function in particular is still going to be very useful. Okay, so next I took a look at how I could apply almost always auto to the functions that I have. And the general guidelines that I followed were using auto for any circumstance where I wanted to return a local variable or an R value. And if a function has multiple return types, then the auto will be deduced as the common type of all return statements. I didn't really have any getters in this example, but if I did have them, then I would use an L value reference to auto for those as the return type. And then for any functions that simply return the value of calling another function, basically forwarding functions, I'll use decal type auto. So that way if the function that I'm calling happens to return by value or by reference, it'll pass that directly through as the same type. And then finally, if I needed to sphere anything, I prefer to use auto, even though it doesn't really bias anything here, just to kind of help to corral the sphere statement out of the left-hand side and after the parameters. That has a nice side effect where if you want to use expression sphere using the parameters, you can do that by moving it there. I think it just looks nicer to have it on that side. So the first thing that I did was to try to take an opportunity to look at the common patterns that were already in the code. You may recall there were multiple instances where I had defined uniform int distribution. So I said, well, let me see if I can do more deduction here by creating a helper function. I've called it makeUD here just to keep it on the slide. And what this does is it takes 2 template parameters, A and B, which can be different types. It will then deduce the common type of those and pass that as arguments to the D type here, which is the uniform int distribution. You may also notice that this sphere is based on whether or not the common type is integral. So you could imagine defining an overload for this, which sphere is based on whether it's a floating point type, and then you don't have to worry about typing out uniform int distribution everywhere. So I like that approach. So here I've updated the functions to apply the rules that I just mentioned, as well as to use the makeUD helper function that I wrote. The logic is all the same, but it has most of the types removed. The only thing that's really still visible is the parameter on the heal and the hurt function, which isn't shown here just for space reasons. So I think I could do one better for the selection of a random spell. I really want to pick a random element in the range. Since I have an array to work with, I might as well have a function to do that. So C++17 has another function coming in that's going to allow you to select n elements from a range. But in this case, I just want something simple. I just want one. So I have the begin and end of a range, as well as the G is the going to stand in for the uniform pseudo-random number generator. And then I simply figure out how many elements there are between the two iterators that I passed in, and as I did previously. And then I call stdnext to advance the first iterator that many times. Now I've specified this as an input iterator. You could do that. It would be better and more efficient as a random iterator. So just keep that in mind if you want to use this in your own code. Here you can see it applied to the turn function. It's obviously more code than we saw before, but we don't have to deal with trying to calculate the distance between those two. And everything else is basically the same here. Okay. So you may recall that the functions that we still had for the spells, they still had a parameter with a named type. So I want to take this a little bit further and try to find a way to get rid of that type, to see what it would look like in that case. So the guidelines that I followed for lambdas, I use forwarding auto for any circumstances where I have a lambda that I want to give a name to. I'll use forwarding auto for input parameters. And then I'll use an L value reference to auto for any parameters that need to kind of have their lifetime managed outside of the lambda, like we did with the life. For any lambdas that need to return by reference, I've used L value reference to auto as the trailing return type here, since by default lambdas will return auto, just plain auto. And then for any forwarding functions or forwarding lambdas that I want to use, I'll use the trailing return type of decal type auto to get the same functionality I had with forwarding functions. So I can now define the heal function within the body of the turn function as a lambda. And this gets rid of any explicit types that we had listed in the signature. I had to update this to pass the engine as an additional parameter. You'll see why on the next slide. And I did that instead of just capturing this and passing it through. So because we can now, did my mic go out? Okay, sorry. Because we can now define the spells as lambdas, we can actually declare them as independent parameters of make array. And this, the only constraint that we have to use in this circumstance is that because these spells are all lambdas, lambdas all have a unique type. So I have to cast the lambdas to a uniform function pointer, which I've defined up above the signature for that, just to make sure that if I have multiple lambdas passed into make array, they'll all be considered the same type. Then this is the rest of the turn function wouldn't really need to change any further. So I want to take stock of where the changes that we've done so far. So we've added a good amount of reusable functions that can help to deduce things going forward. But we had a lot of difficulty trying to deal with C-style arrays. If we're really trying to take deduction to its extreme, I don't want to have to get in the habit of defining my array sizes. So utilities like the experimental make array, I think, are going to be pretty useful if we can get those in the standard. As we saw in the turn function, if you want to just add another spell, it's as simple as adding another parameter to the make array function. You don't have to remember to update things independently, which is a nice property. It would be very easy to go in and add another member function that we had earlier and then forget to update the array. This has the property that the spells are no longer visible outside of the turn function. And they're actually even hard to spot individually inside the turn function, unless you're doing something like adding a comment before each lambda. So as far as the changes that we saw that we can actually measure, I counted the total number of types that were in the both versions before and after we started. And you can see that the explicit types decreased quite a bit. We couldn't get rid of all of them because, of course, the member variables that were non-static can't use almost always auto style. And we were able to get most of the types to deduce. The total number of words actually increased a fair amount. And the total number of characters increased, I'd say, substantially. So after running the game for 11 million turns, I measured that the time actually to do that decreased with the almost always auto version. And that was a little surprising, but I think that performance improvement came largely from the conversion to lambdas. We no longer had the complexity of dealing with the pointer to member functions that we had previously. So I want to look at something a little bit more complicated here. So I now have a spell that I want to add to the game, which is going to deal a conditional amount of damage based on the current state of the player. So if you have between 80 and 100% life, it's going to deal 25% damage. Going on down to if you're between 0 and 20% life, we won't actually change your life at all. And you can see here the definition in the non-almost always auto form pretty much follows that pattern that we saw in the previous slide. And the key here is that I wanted to find a way that almost always auto could tackle a common practice of, say, defining the value of life conditionally. I don't want to have to incur the overhead of assigning it a default value to begin with and then changing it later. Now, there's other ways that you could deal with that besides converting to almost always auto, but if you'll bear with me, I just wanted to view this as an exercise of how to deal with this particular constraint. There's sometimes reasons why you can't simply use a helper function to do that. So to kick this off, I'm going to use a variadic function to evaluate all the branches that we had previously. The variadic function has 3 template parameters. If, then, and else. They're all function objects. Else is a variadic parameter pack. So I'll evaluate the if the result that it returns is convertible to true, then I'll return the result of calling the then function. Otherwise, I'll recursively apply the else parameter pack until I run out. And here's the terminating case. And I'm sure if STL is in the audience, he would probably chastise me for using a recursive version of this, but this was on purpose because I want to make sure to short circuit and not evaluate the other branches when I don't need to. You can see an example, a trivial one at the bottom. So if the first lambda, there's pairs of lambdas there, and the first one is the condition, the second one is the result that we'll use if that conditional lambda returns true. So in this example, you can see that the result, because the first conditional lambda returns false and the second one returns true, is that the result is a double of 1.0. And here we've applied that same logic to the branches that we had previously. And this has a nice property that even though it doesn't look like a traditional series of if-then else's, change is only ever assigned a value once we know which branch we're going to take. So choose, I feel like, is kind of like for branches what for each is for raw loops. It expects a regular pattern and will try to help enforce that for each branch that you take. On the downside, just like with for each, the raw behavior is kind of hidden behind the template function. And you can have errors due to mismatch arguments that could be hard to diagnose if you don't have a good amount of static asserts or potentially concepts to help you. The initial version that I had was using a stood pair of the condition and result function objects, which is going to be a little bit safer, but it was a lot more verbose at the call site. So I opted for the version that fit on the slide a little bit better. And then finally, as I mentioned earlier, you could, if you don't want to use something like choose, you could use lambda as an immediately invoked function expression or just another helper function to kind of do that branch evaluation as you see fit. And the overall impact on our code base was that we now decreased the explicit types to 0, and the number of deduced types actually went up substantially, a lot more than we had explicit types originally. And the reason for that is that we have a number of types that are kind of hidden due to all the lambdas that are being used, the lambda type itself, and then the deduced return type for the lambda. The total number of words increased a good amount from 81 to 97. The total number of characters increased a good amount too. But the really surprising thing to me was that the performance was identical. And that was because the optimizer did an amazing job of taking both of those forms and recognizing that they're doing the same exact thing. Okay, so most of our games have multiplayer, so I thought, why not finish off by adding multiplayer support to the game to see the impact that Almost Always Auto has with loops. So we'll change the current amount of life that we have to an array. And each turn, we'll iterate over the array, and we'll skip any element if the life is already 0, if they're dead. And we'll end when all life values are 0. So here's the changes that I made to the non-almost always auto version. I had to omit some other stuff that didn't change just for space here. But at the top, you can see we have a stood array of size 3 for one for each of our players of life. And then I've had to update and add a constructor here that fills in each of the values with the maximum amount of life. That's because the only other alternative is to add braced initialize or a default member initializer afterwards that has one element for each of the 3 life values, and that's not really very easy to maintain, so I kind of prefer using fill in this circumstance. And then finally, I updated the body of turn. This isn't the complete code, but I updated it to loop over the values in the array and apply the logic that we saw earlier. And the spell here, it's not defined, but it's basically just a shortcut for picking the random spell and then calling it. So, if you followed Sean Parent's C++ seasoning talk, it's an amazing talk, he recommends using std for each to try to avoid raw loops. And I've done that here, but because std for each doesn't really allow any output, it's really just geared towards modifying your array. I've had to capture, I had to define the anyAlive Boolean outside of the for each call so that it can persist after the call is done. And then I capture it and update it with the lambda. So this is pretty good, but it does have the downside that we've had to do that association with, explicit association with a bool, which isn't great if we want to update the logic that happens inside of the lambda as we iterate over each element. So I looked at the standard algorithms, and none of them really helped me out here. So what I did was I kind of smashed the idea of std accumulate and transform reduce into this kind of monstrosity. And I've rearranged the order of the parameters a little bit, simply to try to help actually deduce the type of t. And that's helpful in this case because I have a value that I can figure out entirely by looking at the signature of the unary op function and deducing that by providing it with the input iterator and dereferencing that it'll produce the t-type that I'm interested in. So even though it's a little bit different from the order that parameters appear in std accumulate or std transform reduce, I like that you can define it in this way and have that extra initial parameter kind of default initialized. So we'll take the first and last elements in the range, the unary op, which is going to be our transform, and the binary op, which is going to be our reduction, and then just simply iterate over the range and apply them, and then return the result when we're done. Here it is applied to our turn function. It's a lot more code now. We have the begin and end of the life range as the begin and end parameters. Then we have the lambda that's going to be our transform function. It's responsible just for checking to see if the life is, the current life value that it's iterating over happens to be greater than 0. And if it is, then we'll call the spell function and finally return whether or not that particular player is still alive. And then at the bottom we have our our reduction lambda, which will take the value that we've been accumulating over time and the latest result that we just calculated and reduce them together. And you notice I didn't have to specify the initial value here. It can completely deduce that because of the type of the transform lambda up above. So that would start it off at false. So overall, I felt like if you try to avoid raw loops and you're trying to use almost always auto style, that's going to require a bunch of additional work to try to understand how to make that function properly. Most standard algorithms don't really want you to try to mutate the contents of the range. Some of them don't even let you invalidate iterators. It would have been nice to use a function like std any of here, but unfortunately that wouldn't work because it explicitly says that the range shouldn't be modified. So a QMutate, unlike std transform reduce, can figure out the type of the t parameter and default it. So I think this just kind of highlighted that if you're developing a generic algorithm, that the parameter order is important, and that if you're trying to use standard algorithms, that you have to be very cautious of any potential narrow contracts that they might have. And then finally, just kind of taking a look at the overall impact that the looping changes had. We were able to eliminate almost all of the explicit types that we had. The only ones that we couldn't get rid of are non-static member variables. The total number of deduced types is actually larger than the total number of explicit types that we started out with because of the additional lambdas. The total amount of words and characters both increased substantially due to all the extra lambdas that we had to use. And this is a little surprising. The performance is slightly slower with the almost always auto version. The optimized assembly is pretty close, but not identical. I think there were probably one too many layers of lambdas for it to kind of chip all of them away. So here is kind of my overall takeaway after going through all these examples and trying to see the impact that they had. I'm not going to read through all of them, but I think these kinds of properties are important for you guys to consider when figuring out if almost always auto style is the right thing or not for your code base. And since I think we're running a little bit early on time, I have a couple of bonus slides after this, but sorry for the formatting mess up there. But if you want to take one thing away from this talk, it's that more typing for less typing if you use almost always auto. That was kind of something that my coworkers and I joked about. So just keep that in mind. And before I get to the bonus slides, I do want to thank a bunch of my colleagues for providing some great feedback on this. And there's a link to the GitHub repo that has all the code that I developed. I'll take questions first, and then we have time. I can go over the bonus slides. That's all. No questions? How many people use almost always auto? Okay. How many of you who were kind of on the fence feel like you're more interested now? Okay. How many are less interested? All right. Fair enough. Thanks for your honesty. Go ahead.
Could you expand on your reasons for using auto-ref for local variables as opposed to just auto? Or...
Yeah. The main reason for that is to work with types that are not movable or not copyable. So it works nicely with unique putter, shared putter, proxy types as well. Like if you're trying to iterate over a vector of bools or a bit set, you don't have to deal with any problems of not being able to do that correctly. It just kind of works universally, which is nice. Any other questions? Cool.
So this seemed to have a lot of boilerplate due to the lambdas and trying to put everything into stuff that looked like standard functions.
Yeah.
So my question is, how much of that boilerplate do you think would have gone away if you'd been, I guess, less extreme about the always almost auto and used auto everywhere that it was, say, easy or not writing a bunch of boilerplate, and how much of an effect would that have had on the code base over trying to force it as far as possible,
Right.
Which, may be why it's scaring people off from this talk and that kind of stuff.
Yeah, I mean, my intent in going this far was to see what it looked like when you do apply it to this extent. I don't think anybody is necessarily advocating that you go that far, but I wanted to see what it looked like. And it was interesting that as I continued to try to push things, I felt more and more like leaning towards generic algorithms was helpful, or trying to develop additional ones. That was a surprising result. I wasn't really expecting that I would develop a bunch of helper functions outside of the scope of the talk necessarily. I wasn't even trying to do most of those to show as examples, but they ended up being useful. So, go ahead.
Do you really write code like this in production?
No. This is admittedly a toy example. I think we're on my team, we're starting to look at how to practically apply almost always auto, whether or not to even do it. This was an exercise to try to help me understand the impact. I've shared it with folks on my team, so I think they can feel more comfortable with the idea of even trying to do this. Before it really did, I went through this exercise. I think a lot of people were very understandably apprehensive about the potential impact that it could have on readability versus flexibility. So I think, I went very far along the scale, probably farther than Herb would want me to go. But it was an interesting exercise. So, go ahead.
Perhaps the answer to the last question is made this a bit moot, but how do you overall feel that this has affected the readability, maintainability of your code and the productivity of working on it?
I think I've seen cases, aside from this toy example, I've seen cases where it actually has helped quite a bit, as we have a lot of cases where we're trying to convert from, say, our own custom containers to something like standard library containers. And by trying to leverage almost always auto more and more, we don't have to worry about updating so many places, at least in terms of the simple syntactical change to convert from one named type to another. Obviously, you still have to worry that the interface is compatible, but if you tackle your conversion project in good phases, I think you can do that. Go ahead.
Well, I think the recurring theme that I observed in your talk, it's more code. Every step it's more code.
Yeah.
And I think everyone will agree that it's a lot less comprehensible at the end. So I would like to coin the term almost never auto.
Doesn't quite roll off the tongue as easy as almost always. But I can appreciate where you're coming from. I think the complexity of some of the tricks that I've pulled here is probably beyond what most people would recommend. Go ahead.
Could you go back to slide 27?
Sure.
So you have a comment that says that the return of the lambda is a double, but
Yeah.
could it also be a float? And if it could, then at that point, is it possible that other types could be incorrectly deduced? And how would that affect code?
I'm not sure how it could be a float in this case. It's the common type of both the first result, which is returning an integer, and the double, which is the second result.
Okay.
Maybe I misunderstood your question.
No, I think that was it.
Okay.
I wanted to mention a case where you didn't go far enough with auto. This one's good, but actually 34 I think is maybe a little more compelling. Yes, yes. So here you actually have explicit typing,
Yes.
even though it looks like everything is deduced. And
Yes.
it's hiding in the decal type.
Yes.
And previously it was also hiding in the result of. And the mistake here in highly generic code, which I would worry about in the standard library, although it would probably never occur in application production, is you have asked the question, what would happen if I invoked unop or uop on dereferencing the iterator and the value category matters? Your actual invocation uses uop as an L value always. But if you've been given an R value, the decal type is asking, what if I invoke this thing as an R value? And those can now give different answers with ref qualifiers.
Yep.
So a sufficiently motivated attacker, in some sense, can force you to deduce the types incorrectly because the T asked the question not with auto, but with decal val forming it through a different path. So here you didn't go far enough with auto.
Thank you for pointing that
That
out.
is very subtle.
Yep. Any other questions? I can show you some bonus slides if. So one thing that I ran into while trying to develop this talk was difficulty with trying to pass templated functions through to standard functions. Like in this case, if I want to calculate the maximum value in a range, you could use std_max_element to do this, but I wanted to find a way to deal with the fact that if I were to try to pass std_max, trying to explicitly qualify it is ambiguous. So I didn't really have a way of trying to deal with this in a case where I wanted to deduce as much as possible. So I realized that I could use a variadic generic lambda to actually capture the function that I'm interested in using and use argument-dependent lookup inside the lambda to actually forward it through transparently. So this way, whatever I pass in to std_accumulate, it will be passed through directly to the variadic lambda that I have here, and I don't have to worry about trying to qualify max with an explicit type. So I found this to be useful. It's a lot more typing than using std_max_element, obviously, in this case, but I think it might be useful beyond that. So if there's no more questions, thank you all for your attention and for not rushing the stage to attack me with torches and pitchforks. So, thank you.